So we will have our first exam on Friday in here. Let me just briefly list the topics and then I'll open it up to questions you might have. So we started out with a review of digital logic, so and, or, and not, and then we looked at memory kind of as a concept. There are two numbers associated with memory. There's the memory address, and then the data stored at that address or location. And we looked at representation of numbers and characters. In particular, we looked at the 2's complement representation of numbers. So make sure you know how to take the 2's complement of a number, for example. And then we also looked at the ASCII data representation of letters and punctuation. And we looked at 2's complement arithmetic, where essentially it's just binary addition, but when you represent negative numbers using 2's complement arithmetic, you actually get signed addition. If you want to do subtraction, you'll need subtractor circuits. We just actually take the 2's complement of the second number and add. We looked at switches and LED interfaces, so I'm pretty sure there'll be a problem related to that on the exam. Then there was a very brief introduction to the C programming language. I think it was just a section on that. And it was very brief because it's assumed that everyone has previous programming experience, perhaps not in C, but something like C. And then we spent a lot of time, in the last couple of weeks actually, on assembly language programming, covering the syntax of the language. There's a label, an operation or mnemonic, and then with operands. And we looked at different addressing modes, memory access using the LDR instruction, logical operations, and or as mnemonic devices to and or register contents, or shifting operations. We had logical shifting and then arithmetic shifting. And arithmetic shifting actually retains the sign bit as the difference. And then we looked at the different arithmetic operations. More recently, we looked at the stack, storing values on the stack. Just last time we looked at control flow, how you can implement, how loops and decision structures are actually implemented in the assembly language. We talked about the calling convention, how you can write functions in an assembly that you can call from C, or vice versa, how you can call C functions from assembly language. Where are the arguments passed? Where are the arguments? How are the return values passed back? And then we also talked about a little earlier ARM architecture. Basically, a number of registers, how the various registers are used. Okay, so the exam will be open text, but not notes. And primarily, it's open text so that you have access to all the assembly language instructions in the back and the documentation for them. So hopefully you'll know most of the other material. Are there any problems you'd like me to go over? Homework problems? There was homework due today, is that right? How was the last problem I gave on Monday? Did you get through that? That would be a good one to make sure you understand before Friday. Because it's got the calling convention, it has you accessing numbers from an array, so accessing data in memory, and then it also deals with control flow, in that case, how to implement a loop in assembly language.
Did you feel that one?
Yeah, we can work through that. So typically what I do is actually start in a high-level language for the algorithm, in C or some pseudo language or something like that. So in that particular case, you were asked to add up the elements in an array, right? And so I think the prototype for the function we're trying to implement would be the address of the array is the first argument, and then the length of the array is the second argument. And you have to know that order is important because that address is going to be passed in R0. The length of the array is passed in R1. We need to return the value in R0. And then, so, kind of our, way you do this in C, perhaps, is you set the sum equal to 0 while n is greater than 0. You can do it with a for loop, okay, whatever. Sum is equal to, now what I want to use here. So this is kind of C syntax for get the value at this address and add that into sum. And then now we need to decrement n and then increase our address by 4 bytes because we're adding integers here. And that is another difference between assembly language and C. When you increment a pointer in C, for example, it would automatically, if it's an int pointer, it would automatically increment the address by 4 for you. If it's a short, it would increment it by 2. But at the assembly language level, you have to keep track of what the objects are and their size, and actually increase the address by that value. So that's kind of the high level implementation of it. You want me to actually code it or just do it in Code Composer or just do it on the board?
Whatever works for you.
It's probably going to be a little quicker on the board than bringing up. So, what the our function has to be labeled. Okay, so we can call it from C. And then furthermore, we have to declare it as a global so the linker can find it when it links, our C program is actually in a different file. So, and then we can try to do everything in just our scratch registers. Okay, so typically one of the things you want to do is though although it's not necessary here, but it's good practice, is to push the link register. And that's important if you call any other functions. We don't really need to call any other functions in this function, so it's not necessary here, but it's good practice to get into. Okay. And then, so I'm going to initialize. I'll use R2 as our, I guess it's MOV, as our sum register. And usually I try to keep track, with some sort of notation over here that's got the register name and the variable in the high level language. So I'm reminded as what R2 is always containing. As long as I'm just using R0, R1, R2, and R3, I don't have to save those values. The function that calls me, if it wants to preserve those values, it needs to save those. Okay. But if I change any of the other registers, I need to save those and restore them. And so if I find myself needing to use R4 or R5, I would push those onto the stack as well, and then pop them off. Okay. So now what we can do is I'll have a beginning of my while. Okay, so that needs to be labeled. And then what I'm going to do is actually just compare n, which is an R0. So you might put that up here. I'm sorry, the address is in R0. R1 is n. R0 is my array pointer. So compare R1 to 0. That's this part. And if it's equal to 0, I want to jump out of my while. So you don't have these high-level constructs like you do in C, and generally, so if they're equal, this would be the continuation after my while loop. And then now, there's several ways to do this addition, but I'm keeping my sum in R2, and I want to actually use the address that's in R0. That's the one that holds my address. Okay. Now is that okay? R0 holds the address of the first element of the array. That's how you pass an array in C. It's passed by pointer. Okay. So in the main program, you would just call this with the name of the array. But what happens there is actually it's the address of the first element is then copied into R0 before this function call. So then I've got a decrement n, and then I increase R0 by 4. There's actually special syntax to automatically increment R0 here. If you look in the add instruction. So I know these instructions are so this uses the general and he's got some examples down there at the bottom. Oh, that's not going to work. I have to actually, you can't do that. I have to actually load the, I have to use LDR to actually, So I still have R3 available. To load the value into a register. I can't directly access memory and add that to a result. Some microprocessors allow you to do that. So, and I guess it was actually and so I could leave this like this and then increment R0 later by adding to it. But you can also do this. So, and if you look at the instructions for the LDR operation on page 445, it loads the 32-bit address from, so this is an example, like 3 lines from the bottom of the page. It's got LDR R3, comma, brackets R7, comma, immediate 4. And so this actually will get R3 is equal to the array element, and then R0 is equal to R0 plus 4. Okay. R0 is my array pointer. Now, there is a way to actually increment the address beforehand. Okay, that's not what I want here. But if you move the number inside the brackets, going up a line, it will actually increment the address and then load from that new address. And I don't have to do this. I could just have right below this and add to R0 4, and that would increment the address. But I can, it's built in, saves an instruction. Okay. I can do it all in one instruction. Okay. So now R0 is pointing to the next element in the array, the next time I come through the loop. And then what I want to do is subtract 1 from n, and I could do a compare under this, but I could just go ahead and do a subs instead, which will cause the flags to be set. Okay. In particular, I'm interested in is the 0 flag set. And actually, I've got my compare up here. I can move my compare out of my loop since I'm using subs down here. So this is actually going to do the compare to check to see if n is 0 when we pass it in, okay, which it could be, in which case we're not going to add anything. But now I'm going to subtract from R1 1.
Why are we setting flag up? I don't understand.
You have to set flags to do a branch. Okay. And so I'm going to loop back and do that and then check.
So once it hits that flag, check back.
Yeah, so this is now set. So if R1 say is 2, this is going to subtract 1 from it. That won't set the 0 flag because the result is 1. This will only set the 0 flag when R1 gets to 0. Okay. Which now I'm just going to do a branch back to my while. This won't alter the flags. But the first instruction in my while is check to see if the result of a previous flag setting is 0. And if it is, I'm going to jump out of my while. And the last thing I need to do is actually move my sum, which is in R2, into R0. That's required by the calling convention because the return value, this thing, in C, the way I would call this is, sum is equal to add array, M, and then length. Or in the driver program, I think I gave you int M is equal to a small array. Okay, so this is setting up an array of integers, initializing first element. The 0th element is 10. The first element is 20. And then you can have a length here is 2. And then call this, and it should return sum would be equal to 30 in this case. Okay, so this is the C. And then this is the assembly language implementation. This would be, you know, the kind of the C level implementation of this function. Now, the other thing that we need to do here to finish this up is pop the link register. And I could actually erase both those lines. It's not required here. And then is it, no, it's not BL, it's BX. Back to the link register. BL is the call on assembly, BX is the return. So can't guarantee this is correct. I mean, typically, you know, what I would do is the first step when I'm building this in code is probably, you know, have my function do nothing more than print the first element of the array here to make sure that I'm loading it correctly and I've got access to it. You know, and then you just return 0 at like the first implementation, and then, you know, continue to build on this checking to make sure that it's actually, you know, correct throughout. So, does anyone see any mistakes? Any questions about what's going on there? Completely lost? Okay. Make sure you know how to do, one of the things we'll be doing throughout the rest of the course is some basic testing of bits and control registers and setting of bits. So let's say I give you the problem, if bit 4 in R0 is set, call the motor on routine. So, say I gave you that problem and asked you to implement that in assembly. I'm going to put another restriction on it. Leave R0 unchanged. So I'll give you a few minutes to So when you're setting or testing bits, you know, you typically going to use and or operations, okay, to test and or set. So you know, with the S subscript on, maybe the and or actually set the flags appropriately. another one. Set bit. So my bit numbers are bit 31 to bit 0. So bit 4 is actually, you know, the 5th bit in the binary number. So set bit 31. And R1, leave all other bits unchanged. And this is another common operation. When you want to set a particular bit in a control register, you often have to read it, set the bit you're interested in, leaving the others unchanged, and then write it back. So, give you a few minutes to work on those two problems, and then we'll. Did I do enough here? This, I think, to come up with something like this as an answer to the homework. Yeah.
For the like branch of equal, shouldn't that be like branch of 0?
I think they're equivalent here.
Okay.
Branch of equal is the same as if the two numbers are equal. So it's essentially a comparison. And if they're the same number. So it could be either. And in this case, yeah.
Because wouldn't it only be equal, R1 is equal to 1? Or is that what you want? That's the,
It'll be equal when R1 is equal to 0. Right. So, and I was testing as long as n is greater than 0. So when it gets equal to 0, I want to jump out of the loop. So it's the issue, you know, with 5 elements in the array. You know, n is 5. I decrement it 5, 4, 3, 2, 1. That's my 5 elements. When it gets to 0, I want to skip the loop. This is equivalent to BZ2. It'll do the comparison. They're both 0. That's what I'm testing.
how does it know it's comparing to 0? I'm just.
Oh, you mean in the comparison or down here in the subs?
In the subs.
In the subtraction, once I subtract 1 from R1, it'll be 0 in that case. And that will set the 0 flag. Oh, you're right. They'll be equal when R1 is 1. So it's probably easiest just to leave the compare as part of the Y ordinate. Because that will do it. Subs. Or change that to BZ would have worked. Yeah. Because the equal, the way I had it, would have been true only when R1 is 1. I would actually want to test when R1 is 0.
Thank you.
Actually, there is no B. Branch of equal is what we have. Right? Look, I'm looking on page 436. So branch of equal is actually if the 0 flag is set. So it's not that the numbers are equal, but if the result is equal to 0. So not the two numbers, but if the result is equal to 0, that's when the 0 flag is set. So either way, I could subtract 1 and not set the flag and do the comparison. But branch of equal is not actually, well, it does test if the numbers are equal in a compare, but it's really testing to see if the 0 flag is set.
So it'd be like R1 is equal to 1, so 1 is subtracted, in which case they are equal. The answer is 0.
Right, after the subtraction, the result is 0, so the 0 flag would be set. It'd be the same if I left this S off, did the subtraction, and compared to 0. At least I think. We'd have to code it and see what the microcontroller actually does, but I think that's right. There are a number of different ways to do that, actually. So. Okay, so typically if you want to test to see if a bit is set, you want to and then since I say here, don't change R0, so we need somewhere to store the result. And then bit 5, as that would be actually in hex, hexadecimal 10. So bit 4, B0, 1, 2, 3, bit 4, then is in the fifth bit from the right. Now, here again, this won't set the flags. So after this operation, R1, and this is a 32-bit AND, R1 will be 0 only if that bit is 0. After this AND, R1 will be non-zero and it will be equal to hexadecimal 10 if that bit is set. All the other bits are irrelevant, right? Doesn't matter what else with this ANDing. You know, if I AND these two, I'm going to get zeros everywhere. But if I AND those two, I'll get a 1 and zeros everywhere else. So you typically use ANDing to test to see if a bit is set or not. So doing this ANDing stores the result in R1 and then sets the flag. Okay. And so we want to take the case if it's equal now. I want to skip my call routine, branch, link, motor on, and then I would have my continue label. Because if the result is 0, it means that flag was not set. I want to skip the call. If it's not 0, again, you could do this differently, branch if not equal down to some motor on, but I think this is a little cleaner. So call motor on, and then after that routine finishes, we'll return right back to the next instruction. Questions? Yeah.
Do you not need to like compare R1 to the X10 at some point, or does it just like compare them automatically?
So that's what the S does versus the AND. Okay. So the S says, set my flags based on the result. So, and I really just need to test to see if the thing is 0 or not. So yeah, it's a, alternatively, you could leave that off, put in another compare statement here to compare R1 to 0. But you know, that's such a common operation that they extended, that they kind of built that capability into most of the operations. And then you can, you know, set the flag appropriately if the result is 0. And that's true for most of your arithmetic operations as well. You know, you can test to see if a result, if you add the S onto an adds, you can check automatically to see if the result is 0 or if there's an overflow without actually having to do any sort of compare operation, additional instruction. You know, and you can extend this so that, you know, you can test to see if 2 bits were set. Just by ANDing with the appropriate, you could test to see that, in that case, that, well, with an ANDing, it would be testing to see if either bit was set here like that. Set bit, the way you set a bit is with the OR operation. And bit 31, that's the most significant bit of hexadecimal. I could use decimal, but it's a lot more convenient when you're working with bits to use hexadecimal because of translation directly to binary. I don't have to convert that to the decimal equivalent, right? You know, here I could use either 10 or I could, and this should have that immediate sign. I could do it like that. It's the same number, decimal 16, but typically when you're doing binary operations, it's easy to think about the bit in hexadecimal and directly translate to hexadecimal. Okay. 8 is 1 followed by 3 zeros, and then 4 binary bits. And then so this is then the 32-bit word. ORing, this won't change any of the other bits, right? It would just change, toggle that most significant bit in that 32-bit word, because 1 or 1 is 1, 0 or 1 is 1. So it doesn't matter what that bit is. If I OR it with 1, it's going to set it. ORing with 0 won't change any of the other bits. 1 or 0 is 1, 0 or 0 is 0. So nothing else has changed when you OR with 0. If you OR with 1, it's going to set the bit. An exclusive OR would toggle all the bits. Be one way to do it. Or you could just take, there's a, just take the negative, the complement of all the bits, the not. Any questions? Not getting good feedback here. You guys feel ready for this test, or no? But you wouldn't feel ready no matter how much time I gave you, right? So.
That's just my favorite problem. All that stuff.
Yeah. Yeah, it's not easy thinking at this level. compared to working in C, where you have to, usually there's kind of 2 branches associated with every operation, skipping over stuff, branching back. Is that the part that's confusing, or just knowing what the operations are?
It's just like the syntax top bit as well.
Yeah. There aren't a lot of operations here with this particular microcontroller, unlike the Intel ARMs are essentially reduced instruction set. There aren't that many instructions compared to the Intel processors, which have hundreds of different instructions. So LDR to load from memory, STR to store in memory, then you get your basic mathematical operations. They do have a lot of different, variations on them. That S subscript, and then something that'll take either 2 or 3 operands, or and the last one can be, an immediate operand, or it could be a register. Any questions? All right, I don't want people running up here when I say we're done and asking a lot of questions now. So now it's the last chance. Yes.
So in that array, if you would use like R5 and R4 and R5, would you have to push and pop each one?
Yes, you should. Yes. My answer is yes. Okay, because that's actually part of the standard calling convention. So, the issue is, whoever calls that array, they may have something stored in R4 and R5. And if you change it here, that information is lost. So as part of the standard calling convention, if you change those registers, you need to restore them. So that, again, that's completely, it's not really arbitrary because it is a convention now, but they could have, chosen to allow you to use R0 through R6 as scratch registers. In some books they'll call them callee save versus caller save. Here the callee add array is the function being called, the callee, and C-A-L-L-E-E. But here the callee saved registers are R5 through R14. The caller saved registers have to be R0 through R3. Those are the scratch registers. Those need to be saved by the routine that's calling us if it wants to preserve them. All right, that's it then. Yeah, no, I think I somewhere I had, it may have been in the lecture, but I had a link to, I provided the main route, and you just had to write this up. Doing everything.
Yeah, that's what we got there. Yeah.
Yeah.
Send
I'm
something
going
to
after physics,
Was
right?
it?
Yeah. Thanks, like I got everything. I got them for lunch, but I got my other stuff on the school.
Do you have class now?
And we didn't use the EQ.
I don't know if we beat because the way we didn't use the
It's gonna count. It's gonna count over time. And like, you'll be able to see if we have errors, and you can go up and down, or you can add it, and then we get traffic file, like, very much, error 1, error 2.
The issue is I don't understand that.
So, something that we file, something candidate. And so I just wanted to let you know now, but, if I can come in tomorrow,
Yeah, that'd be fine.
okay, tomorrow, and just get it somewhat working, because I'm facing the same issues. So at first I thought maybe it was, out of the draft one, it's an issue with code closure keeps happening, so it won't, whenever I build it, if it's not building, so, there's no pain. That's the biggest thing.
Okay, so, so on this one, I provided a main,
Yeah,
and this doesn't have the other UART routines. So where is this main?
yeah, exactly. I can't find it. That's the issue.
Okay, let me. It's really odd. It is. Let's see.
Yeah, the workspace.
Yeah.
That's the top one. And then,
Workspace. Okay, so somewhere this is not even. I didn't even see it there in the workspace, did you?
no,
Okay, so it actually did not create this in the workspace, which I think is part of the issue. It actually created it in the desktop.
okay.
So do you have anything, probably, we want to just delete that, but let's see what's going on here. Okay, so this is saying this is your default location, which is not where you thought it was. And that's okay, but I don't know where the UART files are.
Okay.
Do you want to use this location?
I can fix this.
Yeah, you just need to uncheck that and browse to, where your workspace. So this is actually where you want it, right?
Yeah.
It says that already exists in the workspace, so I think you probably, it's confused by this one overall. I don't know what the issue is. Looks like you actually changed your workspace. This is where we want it to be. So it's going to restart, but yeah, I think you can stop back in my office tomorrow, but I think it's got confused. You've got files in 2 different workspaces.
Okay. All right. Thank you so much.
Mhm.